on Folman, right? Yep. Who will talk about wave-particle duality up to quantum gravity. Please. We can't hear you.
Can you hear me?
Yes, now we can.
Great. So I hope you can see my slide. I'm now moving it to presentation mode. I hope you can see it now in presentation mode. Is that okay?
Yes. Yes.
So hi everybody. Sorry I can't be there in person. I was in Brazil in July and it was absolutely fabulous, and I hope to be there soon again. Thank you very much for the invitation to speak to you. And it's really a fascinating topic, and we just heard a fascinating talk by Marcus. And so I really expect that we will see in the near future some very exciting advances. So my title is, Can a Rock Be a Wave? From 100 years of De Broglie's wave-particle duality all the way to tests of gravity-related or the quantum gravity interface. All right, so let us begin. So the outline would be a very short motivation. I'm sure you're all very familiar with the different motivations. A quick reminder of what I mean by De Broglie's work on complementarity, and then a quick reminder of Stern-Gerlach interferometry, which is going to be our main tool in the experiments that we are conducting. I'll also show some new results just from the last few days about experiments with Stern-Gerlach interferometry related to gravity, but still with rubidium atoms. Then a quick reminder of our main tool in the lab, which is the atom chip. What is the sequence that we're planning? And going back to De Broglie, what is the decoherence and distinguishability that we have to fight? Only if time would permit, I would also give an anecdote about De Broglie, another work of De Broglie, which is the pilot wave, or Bohmian mechanics, as it is called today, which is a less known part of his work. If we have time, I will also say a word or two about that. As you see in the left side, we're interested in diamonds, nanodiamonds to be exact. They have one spin, that's an NV center, a spin of one in the middle of the carbon lattice. And so in principle, the challenge is to go from our current rubidium experiments, which is 10 to the minus 25 kilogram, to 10 to the minus 15 kilogram, the nanodiamond that we hope to be able to put into the interferometers. So it's a jump of 10 orders of magnitude, which is never easy. All right, today I will not talk about quantum technology, but since it is of interest to many students, and since it's half of the volume of work that my group does, I will say a few words about what we do in terms of quantum technology. So first of all, we worked on compact cold atom clocks. You see here in the bottom left such a clock with a pyramid mode, and you see here a red dot, which are the atoms in this pyramid mode. All this is very small, and you see here a real picture from the lab. Only one of the clouds is the real cloud, and the others are just reflections. And here you see a picture of the outside chamber. It's very small, and it's very interesting to build these kinds of very small devices. We're also doing optical standard clocks. Here we're part, you see in the top right, part of European consortium to redefine the second. We're building an ytterbium clock. You know that most of these clocks are strontium or ytterbium, and we have an ytterbium clock. We also build magnetic sensors. You see here on the right side in the middle, handheld, all optical, vapor magnetic sensor that we have delivered to the industry. And we always try to combine between fundamental science and technology. So for example, while we were developing this magnetic sensor for the industry, we were also working on magnetic sensors for dark matter detection, and you can read all about it in this recent PhysRevD paper. We're part of the known collaboration, which is trying to detect dark matter through these magnetic sensors, or rather co-magnetic sensors, which are more sensitive. Okay, our two recent papers on technology, very quickly. One is a chip scale point source Sandiak interferometer for phase space squeezing. You can find it on the archive. And another one is together with NIST about geometric phase amplification in a clock interferometer for enhanced metrology. This is another nice example of how technology and fundamental science come together, because before we could write such a paper of technology, we had to first understand what is clock interferometry and build a clock interferometer. And after that, we had to understand what is a geometrical phase and measure the geometrical phase. And only that, then we could put it into practice in a technology-oriented paper. And of course, our former students are going to the high tech and actually forming their own companies, and we're very proud of them. So I just give you here a few examples of two quantum computing companies that have just recently been formed, and our students are there, and it's very nice to see how they utilize the knowledge from the lab in their companies. Okay, back to our topic of today. We want to take a nanodiamond here that you see on the top right and send it through a spatial interferometer. And so you see here the two wave packet, and then close the loop in space-time and see some kind of interference pattern, because without an interference pattern, you can actually not have a proof that there was a coherent superposition of your object. So this is the only way we know how to prove that there was a special coherent superposition, and so we would like to see an interference pattern. So motivations, as I said, I will go very quickly through them, but testing quantum mechanics in new regimes, testing the continuous spontaneous localization model, testing exotic theories like the fifth force, exotic gravity interfaces like the DOC-Penrose collapse, self-interaction. There are many exotic models out there that everybody would like to test, not only us. And of course, there are beautiful papers coming out. This paper I particularly like, on how to prove that gravity is quantized by having what you see on the bottom left, having two spatial interferometers side by side simultaneously, and then the two closest approach of two wave packets from the two different interferometers. If gravitation is the dominant force, and at the end you have two nanodiamonds here, yes, two interferometers, one nanodiamond each interferometer. Here at the bottom you do a bell-type measurement on the two spins, and if you see entanglement between two spins, it can only have come from the gravitational interaction. And the claim is that an interaction that induces entanglement, quantum entanglement, must be quantized. So the question, of course, which Marcus described very beautifully, is, can we split a large mass? This is an unknown. And to think a little bit about it, we go back 100 years to this gentleman here, De-Broglie. It's actually exactly 100 years to his thesis. And he taught us, of course, that there is something called complementarity, and that wave-like properties and particle-like properties, it's a zero-sum game. And this could also be written as visibility square plus distinguishability square equal 1. Some call it Witch path information. By the way, De-Broglie talked about other things, which we'll not talk about today. He believed that quantum mechanics is incomplete. He talked about bulk frequency, sometimes called also the Compton frequency, about the pilot wave, which I mentioned before, and so on. Okay, ideas for splitting massive objects. There are quite a few ideas going around. For example, you've just seen in the previous talk this idea about using optical potentials to work on the wave function of a single particle and to stretch it and then maybe even see some kind of interference pattern. So this is the use of optical potentials. This is a recent paper. One of the authors, as you see, is Marcus Aspelmeyer, who just gave the talk, and Orel Romero-Izard, and so on. There is also this idea from the group of Marcus Arndt, who will speak here tomorrow, and he holds the world record for large mass interferometry, which is now something like a molecule of 2,000 atoms. And you could see in this paper that is now by now 2 years old that this is about a grating or Talbot-Lau interferometer, and other people, other groups like Hendrik Ulbricht, Andrew Geraci, and others are also attempting to see non-classical states with similar configurations. There are more ideas, like this idea of entangling masses. We already heard about that. And also an idea coming from Berkeley about entangling between an atom interferometer and a large mass that is in a pendulum. I think that suffices for examples. The route we decided to take is a different route, and that is to use the Stern-Gerlach force. Recently, there was a paper in Quantum magazine where you can read all about the history of what they call the overlooked experiment that revealed the quantum world. I like this article very much. They also speak about our work and how the Stern-Gerlach effect, the Stern-Gerlach force, is now being used to test quantum gravity or the quantum gravity interface. And so I think it's a good read. You could actually also visit the original building in which Stern-Gerlach worked. It's still standing in Frankfurt. And in 2019, it was actually declared a European Physical Society heritage site. Okay, so what do we plan to do? Well, we started to do Stern-Gerlach interferometry in 2013. And once it worked, a lot of smart people immediately saw that you could use it for splitting large masses. And so, for example, in this paper from 2016, they decided, they show that if you take a mass and the y-axis here is time and the x-axis is just one spatial dimension, and if the gradients are working along the x-axis, you see that you can split and you can bring back, and then you can just measure the spin with some microwave. In this case, it's a spin of 1 or minus 1, because that's the spin of the NV center in a diamond, as I explained before. So this is the nanodiamond with its single NV, giving it a spin of 1 or minus 1. And these papers, these theory papers are continuing to come out. They are very interesting, and I suggest to everybody to read them. One of the recent papers came out, you see it in the bottom left, which actually says that the conditions for which we need in such a double Stern-Gerlach interferometer experiment, as I showed before, are less stringent than what has been previously thought. It's enough to get a splitting of a few micrometer, and this is very encouraging. All right, but going back to the Stern-Gerlach experiment, could we even expect it to be able to give rise to coherent splitting? Well, you know, the original signal from 100 years ago did not prove any coherence. Although the textbooks, in your undergraduate textbooks, they sometimes are a little bit misleading, but actually the original signal could have come from a statistical mixture whereby half the atoms come out of the oven with spin down and half the atoms are spin up. There was never ever any proof of coherent splitting with the Stern-Gerlach. So the first question to answer, is there coherent splitting, or is it possible? Well, after a decade of Stern-Gerlach interferometry experiments, I think we can definitely say that such a coherent splitting with the Stern-Gerlach effect is possible. And what you see here actually is a list of experiments from the last decade from our lab, starting from signals that are spatial interference fringes, as you see in the top right, going through clock interferometry, going through geometric phase measurements, and all the way to the last image where we actually measure the spin population, the oscillations of spin population, which is actually what we intend to do with the nanodiamond, with the NV center. But what you see here is all rubidium-87 atoms. Okay, so what have we done so far with Stern-Gerlach? Well, so far we did the top figure, the top configuration is the half loop, where what you see on the y-axis is spatial coordinate and on the x-axis is time. And what you see here is actually the states here, just spin state in the rubidium atom, and the purple areas are just magnetic gradients coming from an atom chip. And so you see here two wave packets. It's just an analog of the double slit experiment. We then let the two wave packets expand, overlap, and we get these nice fringes, spatial fringes. This is the half loop. It's not good enough for the nanodiamond experiment. The main reason is that we don't have a lot of time for this time of flight for this expansion, because decoherence rate is very strong, very fast, and so we need to close the interferometer and measure the interference pattern very quickly. For that, we have this full loop, where we use 4 magnetic gradient pulses to split, stop the relative motion, accelerate back, stop the relative motion, and measure the spin. And this is what you see here in the signal that we obtained with rubidium atoms. So that works. Now, can we do it with nanodiamonds? That is the question. Well, first of all, a few anecdotes. The signal that you saw just before is a very unique signal where the phase is accumulated at t to the power of 3. So t is the time of the interferometer, and t to the power of 3 is quite a unique signal. And it was actually predicted already back in 1927 by Kennard. And we have learned about this from Wolfgang Schleich from Ulm and his group. They did the theory for this experiment, and they actually taught us that if we do this with the nanodiamond, not only with the rubidium atom, we should expect to see this very unique signal. Okay, but that's not the end of the story of this T-cubed interferometer. There are also people claiming that this T-cubed is a very fundamental phase accumulation law. So in this paper from 2019, from Yvette Fuentes, Roger Penrose, and Richard Howell, they show actually that there is some kind of quantum equivalence principle between what they call the Newtonian and the Einsteinian frames of reference, which just means that one is in free fall and one is held relative to Earth or to the lab. And what you see here is again the t to the power of 3 in the phase between these different wave packets describing the same system. So there's something very fundamental about this t cubed in terms of the connection, the interface between quantum and gravity. So very shortly afterwards, in 2020, Vedral and Marletto came up with a paper where they actually call it the quantum equivalence principle. Again, they talk about this 2-cube phase, and what they suggested is that you do such an interferometer, which is a very hard interferometer, where one wave packet, after you split it, one wave packet, as I said, is constant in height, let's say, relative to the lab, and the other wave packet is in free fall, and then you have to somehow join them to see an interference pattern. Otherwise, you cannot measure the relative phase. So we have been thinking how we can actually do that, and we came up with the following idea. And these are preliminary results from really the last few days, where here you see the atom chip, which we use for that. You see here 2 wave packets, the trajectories of 2 wave packets. One is almost completely constant relative to the atom chip or relative to the lab. And the other one does a fountain trajectory, which is actually, it's all the time in free fall. And so this is exactly what was proposed previously by the Oxford people, and we were very curious to see if we could actually close the loop in order to measure the phase, because of course these 2 trajectories are very different, not only in space but also in momentum, and you have to zero both space and momentum, the difference, in order to see any kind of interference pattern. And indeed, from the last few days, we have received these very nice oscillations, which tell us that these oscillations are as a function of the interferometer time, which tell us that we have successfully managed to close the loop, and now we're in the process of fitting it to this theory of the quantum equivalence principle that I told you about before. Okay, now to the nanodiamond. So we use the atom chip for three advantages: very high magnetic gradient, which we need for the Stern-Gerlach force, very fast on-off of magnetic gradients because there is no inductance, because there are no coils, they're just straight wires, and very high position accuracy. So atom chip, very quickly, for those who don't know what the atom chip is, this has been around for the last 20 years. This is an artist view, and in the inset you see how it looks like in the lab. You see actually two clouds here. One is the real BC, and the other one is just a reflection from the surface. This artist view actually is from the group of Ted Hensch and Jakob Reichel, and you see the atoms held in a magnetic trap a few microns above the atom chip itself. And three atom chips already made it into space. One is currently doing experiment in the International Space Station. One just went up to the Chinese space station, and the first one went up through the DLR, the German Space Agency, in a rocket that also came back. It was doing BCs all through the flight. All right, I don't have time to talk to you about the different types of atom chips, but many different particles are now using atom chips, including ions for quantum computing, cold electrons, Rydberg atoms, molecules, and now at CERN, they're even talking about using atom chips for antimatter, for hydrogen, trapping hydrogen. All right. So the nanodiamond sequence, and we hope to start with 10 to the 7 carbon atoms, which means really 100 nanometer particle, and then go up to, say, 10 to the 11 carbon atoms, which would be enough to create this gravitational entanglement, which I spoke of, in 100 millisecond up to a second. What you need to do really is to trap, to cool, and Marcus has described their beautiful feedback cooling experiment, to neutralize it because first it's typically charged, and we need it to be charged for the first Paul trap, and then do the Stern-Gerlach interferometer. You cannot do it with a charged particle because of the very strong decoherence, and so on. So I will not describe this double chip. It's a very complicated chip that does all these actions, but you see here the real design that we're now fabricating at the bottom right. You see different simulations of the trajectories that we hope to achieve with this. And you see some fabrication efforts. This is a double chip that is already being tested in the vacuum chamber. And this is the wire that gives the very high gradient. And these are the nanodiamond, the accurate nanodiamond pillars that we are fabricating to get high control over size and shape of these nanodiamonds. Again, each nanodiamond holding one NV center. But I want to put an emphasis on one very important force, and that is the diamagnetic force. Now, the diamagnetic force is actually working on the carbon atoms, not on, of the diamond, not on the spin. As the mass gets larger, you get more and more diamagnetic force. And the spin is a single spin. It has the same force for the same magnetic gradient. So you are losing the battle as you go up in mass. You're losing the battle against the diamagnetic forces. So you have to learn not only how to fight them, but you have to learn how to use them. And so through different configurations, what you see here in C, different configurations of wires running currents at different times, we have learned how to use these diamagnetic forces. So what you see in A is actually, as a function of mass on the x-axis, what is the relative acceleration that you can get with a certain magnetic gradient. And you see that in blue, the acceleration for the Stern-Gerlach force goes down more and more, while the acceleration for the diamagnetic force does not go down at all. Okay, this is because the force actually increases with the mass. So what we are doing actually is first, what you see in the inset here, a nanometer scale splitting with the Stern-Gerlach force, which you already know how we do. We do a superposition of spin up and spin down, and then we apply a magnetic gradient so that there is this splitting. But this can only give us a few nanometer force. And then you come in with different wires giving different direction of diamagnetic forces for the different wave packets, and you can really now get a splitting of micrometers relative to the nanometers you could get with the Stern-Gerlach force. So I won't bore you with all the sequences that we have, but what you see here is really the diamagnetic potential, and we use these minima of these potentials, of this diamagnetic potential, to push the particles, the diamonds, wave packets away from each other. So now the big question is decoherence. And I go back to the v squared plus d squared, visibility and distinguishability equal 1. It's a zero-sum game. So can distinguishability in this system be avoided? I want to describe very briefly 3 types of D factories that we have to fight. Okay, so what you see here again is the full loop Stern-Gerlach interferometer. By the way, this is a picture from a book by David Bohm, I think 1951. So people have been talking about this full loop Stern-Gerlach for almost a century now. And the first problem, the first D factory, has to do with time irreversibility, because you have to perfectly close the loop, both in momentum and in position, for there not to be any distinguishability. And the closing of the loop has to do with your experimental precision, or rather the imprecision of your experiment to close the loop. And this has to do with time irreversibility, because the second half of the interferometer of the loop has to completely undo the first half of this loop. So some people claim that because of very deep theories of time irreversibility, we will never achieve such a perfect closing of the loop. Now, you have to achieve it to what extent? You have to achieve it to the extent of your coherence length. And of course, the coherence length of cold atoms, like our rubidium atom, is very large, can go to micron scale, whereas for a nanodiamond, it's much smaller. So your precision of the experiment for the nanodiamond has to be bigger. That means much better electronics, less time jitter, less current jitter, and so on. This was actually quantified in the 80s by Englert, Scully, and Schwinger. And you see here, they called it the Humpty Dumpty effect. And they said that your coherence or your visibility is going to drop exponentially as a function of your delta Z or delta P, which are the experimental imprecisions in closing your loop. We also found that you have the Humpty Dumpty effect in rotation. And so this is the inability to close the loop in rotation. This is very interesting. So it's the space of theta and omega, where omega is the rotation frequency. And so in this paper that we published last year, you could find y-axis is the contrast or visibility, and the x-axis is omega t. T is again the interferometer time, and omega is the rotation frequency. And again, here you need cooling, not just like of the center of mass, but also cooling of the rotation, because you see that as omega t grows larger, your contrast drops. And you can understand that through these 2 wave packets, the trajectories of these 2 wave packets. The 2 wave packets on top, the red and blue, are in real space. And you see that we actually managed to close the loop with some sequence. But when you look at the rotation wave packets in the rotation space, or rotation degrees of freedom on these 2 wave packets, so this is just for, this is the sigma, or this is the width of the wave function or the wave packet in rotation space, you see that the loop is not closed. They're far away from each other at the end of the sequence, and this causes orthogonality. Okay, the second D factory you know very well. It's environmental decoherence. For example, BBR. You see that the coherence drops as a function of separation. I will not say anything more about it. Of course, as you cool, you manage to fight a BBR, black body radiation. So you know this very well. And I will go to the third D factory, which I think is extremely important, and this has been calculated by Karsten Henkel, which has to do with the internal environment of the object. We're all used to having decoherence come from the external environment. But here he said actually that as the object grows, the internal environment becomes classical. And if the internal environment becomes classical, it can provide exactly the same orthogonality through entanglement, just like the external entanglement. So even if you external environment, so even if you're in somewhere where there is no external environment, you will still get decoherence, you'll still get which path information or distinguishability from the internal environment. And when we say internal environment, we mean phonons. And what you see here on the top left is that Karsten calculated the phonon modes inside, in this example, a silicon solid. And what he came up with is that in the x-axis is the object size, and in the y-axis is the splitting relative to the object size. And he compared it to black body radiation that we discussed before. These are the full diagonal lines, that even if you cool enough to get rid of black body radiation, you are still stuck, these dashed lines, you're still stuck with internal decoherence. So this is something very fundamental that might preclude future spatial superpositions with large objects. At least it's something that we need to consider and to understand how to fight. Okay, to work with diamonds, you have to know a little bit about NVs and do spectroscopy of NVs. So here you see some papers or some work we did on NV spectroscopy. And I just want to show you this nice picture, again an example of how we always try to combine fundamental science and technology. What you see here are actually vortices. Without scanning, usually to see vortices of superconductors, people have some nanosquid and they scan their tip. This is a wide field image of vortices in real space of a superconductor, where we just put a thin layer of NVs in diamond, very thin layer of NVs in diamond on the superconductor. It was IPCO superconductor, and we could see through the Zeeman effect of these NVs, we could see the field, the flux, magnetic flux of these vortices. And hopefully this could be used for all kinds of technological application. For example, finding cracks in blades of airplane jet engines. Okay, I would like to leave some time for questions. So I will conclude here, but still I want to show you some anecdote about De-Broglie. But before that, I want to conclude the part of the interferometry. And so I think that, I hope I convinced you that Louis De-Broglie and Stern and Gerlach are far from completing their historical role. We can still learn a lot from them. Fully understanding their ideas on wave-particle duality and spin forces may just enable us to create a verifiable spatial coherent superposition of a massive object, and then to test many kinds of things, quantum mechanics, quantum gravity, exotic theories, and so on. By the way, this all is in a levitated system, and this field is called DeVito dynamics, and you heard from Marcus previously about levitating systems. And of course, if this eventually works, this is thanks to the groundbreaking works of many experiments that have been done by brilliant people, like the cooling, ground state cooling achieved by Aspelmeyer and Novotny, rotation cooling by Barker, Stickler, Novotny, Morley and Tet, nanodiamond manipulation, and other people that you see here that made really seminal contributions to this field. If you're interested in this Stern-Gerlach interferometry business, a decade of experiments, as I said, then you could read this review paper that went recently into a book in honor of Otto Stern from the Stern-Gerlach experiment. And thanks to Mark Kyle for putting the material together. And he's now also writing our detailed roadmap for the Stern-Gerlach experiment. Before I say thanks to all of you for listening, I'll take 1 minute to tell you about another less loved idea of De Broglie, and that is the De Broglie bomb pilot wave theory. So, as you know, De Broglie was unhappy with quantum theory, even did not want to teach it at the university. He actually gave up on his pilot wave, which was intended to keep the particle always alive as a particle, irrespective of any measurement. When Bohm came back to it in the 50s and 60s, then De Broglie was very happy to hear about it and come back to it. But I was always thinking to myself, how can we prove that this different language, just a different language, is the same observable, the same expectation, the same predictions? There's no difference in predictions that we know of. So how can we still show that this language is sort of useful for the mind of the scientists? So what we decided eventually to write, and this appeared last year, you're welcome to read about it, and very briefly, is the following. In the De Broglie bomb pilot wave theory, there is a quantum potential. And this quantum potential means that you can actually design a potential that we never measure. We don't know what it is, but we know how to design it. We know the formula for this potential. So we said, can we actually design an experiment in which this object, the nanodiamond, for example, or a rubidium atom, is very close to the chip surface? We always see the van der Waals and Casimir polder. If we bring it too close, it sticks to the surface. We can't take it out any longer. Can we actually engineer a quantum potential that is the exact same shape as the Casimir polder, but opposite in sign? So it will zero it, it will cancel it. And then that particle will hover above the surface and not be attracted to it. So it's an experiment that could be done. And indeed, when we calculated it, and we engineered such a quantum potential, to engineer such a quantum potential, you have to engineer the shape of the wave function of your object. Then what we found here in blue is that if the wave function looks like this wave function in black, this is just the height, the x-axis is the height from, or the distance from the surface, then you get the quantum potential, which is the blue potential. It's scaled down so that it fits into the image, but it's really the opposite of the Casimir polder potential. And if you look at the inset, we really managed to zero out that potential. So this was a theory paper. But if someone does the experiment, and we hope to be able to do this experiment, even with a nanodiamond, we should see that it hovers there and is not attracted to the surface. So I will say farewell to De Broglie with this very nice sentence by Bell, who of course you know from entanglement. He was a theoretician at CERN. And what he said is this very nice thing about De Broglie. He said, however that may be, long may Louis De Broglie continue to inspire those who suspect that what is proved by impossibility proofs is lack of imagination. So I think this is a very nice thing that he had to say about De Broglie. Okay, I have to thank, of course, the students. Some of them, as you see, have moved on. And let me also thank all the theoreticians, the many theoreticians that have worked with us in the past and are still working with us on the nanodiamond experiment. And mainly, of course, thank the students in the lab. And I thank you for your attention.
Okay, we have quite a lot of time for questions, like 5 minutes, please.
Thank you very much, Professor. Glad to
Thank
see
you for the clapping of hands.
Glad to see someone interested in pilot waves these days. I have quite a lot of questions, but I'm containing myself to one. In these kinds of experiments, many people, Marcus Palmeyer and yourself, and many people in the labs talk a lot about trajectories. All of these nanodiamonds, these nanoparticles have definite trajectories, have definite positions why isn't more widespread the use of the guidance equations of De-Broglie and Bohm in predicting, in theoretical predictions of these kinds of experiments? And a follow-up, in the BMV setup, wouldn't the pilot waves and trajectories give any kind of different predictions, given that the superposition of trajectories would give different gravitational fields if the trajectory goes from, the two trajectories go to the closest sides and whatever. Wouldn't the BMV provide an opportunity to differentiate between pilot waves and other proposals? And that.
Okay, so two questions, and they're of course very much related. So I've been reading about Bohmian mechanics, I think, for 20 years, and I've not found anyone who has managed to find, and people have tried. Now there is an issue of timing that people are suspecting that may, timing of arrival of a wave packet, that people are suspecting there may be some difference, but I don't think that there is agreement on that. But in principle, there should be no difference between Bohmian mechanics and standard quantum mechanics. This is how actually Bohm wanted it. And so I would not expect that looking at the trajectories of nanodiamonds or of any specific experiments, we would get any difference. The only advantage I see currently in Bohmian mechanics is the ability to think different. As I said, it's a different language. And so sometimes different language is good for the mind. And in this case, it allowed us to think of a completely new experiment. This experiment with canceling the Casimir polder, we would not have thought about it if we would not have been thinking in this language of Bohm and De Broglie. But as far as I know, there should be no difference in any of the experiments that I discussed. And right now, it's very easy for us to calculate the trajectory using standard quantum mechanics. So there is no motivation to use it. Although, by the way, I did hear some people who are doing numerical simulations. I have heard a few talks about people doing numerical simulations that saying that somehow doing the calculations through Bohmian trajectories was much faster. So that's an interesting statement. We have not seen that ourselves, but some people that doing heavy numerics are willing to make that statement. So that's an interesting statement. But again, I don't expect any different predictions or results.
I have a very short comment and then a question. The comment is that the mechanism of internal decoherence you talked about was called third-party decoherence by myself and Bill Unruh back in 2006. My question is this.
Let me just, who was speaking? Sorry, I could not see.
Sorry, this is Philip Stamp.
Hello. Thank you very much for this comment. So in the in our latest paper, which is I think should be published soon, Karsten and I really did a long historical overview of the quite a few people that have talked about this, and so I hope we didn't miss anyone, including you. But please, if you find that in this paper we have missed some historical facts, and history goes way back decades about such thoughts, then please let me know and we'll fix it. Thank you very much for this comment.
Sure. My question is the following. If you analyze the Casimir effect using a conventional field theory, you find that there's a crossover depending on the distance between the objects, between the non-relativistic and the relativistic calculation. So, and this just comes from the crossover between 1 over r to the 6th and 1 over r to the 7th for a pair of atoms. So how do you work this out using this quantum potential calculation? Because then you have to use some relativistic form of De Broglie-Bohm, which I'm always very suspicious of, in order to get the right result.
Thanks for this question. First of all, you're right to be suspicious, because that was the main argument actually against the De Broglie-Bohm theory, that there is no good relativistic formulation of this theory. But I hear more and more theoreticians claiming that that has been solved. I'm definitely not an expert on the relativistic formulation of the de Broglie-Bohm theory, so I don't want to judge, but more and more theoreticians are claiming that that problem has been solved.
Well,
Now,
if they've solved it, then they should be able to do the calculation correctly.
yes, yes. So, and specifically to the calculation that we did, we have not used relativistic formulations. Maybe we should have. I'm definitely sure that this was a zero-order calculation and it could be done much better. I would be very happy if people do it much better because I would really like to do the experiment. So I would say that this is a proof of concept calculation, and I would be very happy if someone does it relativistically. Yes.
Final short question, please.
Just responding to Philip, there are several theoreticians working on extensions of relativistic formulas for pilot waves, and it is possible to get quantum potentials with relativistic corrections. And beyond that, besides there are arrival time distributions that might have different results from the standard quantum mechanics, there is a long, like 30-year-old proposal of non-equilibrium in pilot waves. So there is a recent work by Anthony Valentini, Beyond the Born Rule in Quantum Gravity, that proposes that exactly in quantum gravity settings, we could find different results, experimental results, between pilot waves and standard quantum mechanics. And that's exactly what I'm working on.
As a function of time, because of non-equilibrium, you mean? Sorry. I didn't hear him. Okay. But anyway, thank you very much for that comment. Yes, I agree that extensions are a new language also offers the mind a possibility to think of extensions. And I hope that extensions do pop up so we can do experiments to try and measure any hypothesized difference between the de Broglie-Bohm theory and standard quantum mechanics. So far, there has been little. And by the way, you remind me of my youth as a PhD student at CERN. I actually wrote a paper about a non-equilibrium de Broglie-Bohm theory and suggested an experiment, which was actually conducted at CERN eventually. We found nothing. But if you're working on it, I think it's a fascinating topic, and I'll be happy to give you the references from my young days working on that.
Okay, thank you very much. Thank you.
Thank you. Thank you very much for listening.
Now we have the coffee break, which unfortunately